let's draw the Lewis structure for molecular compounds or covalent compounds. So that is really important. It's different from drawing the Lewis structure for ionic compounds. So please pay attention. It's like rules. So if you follow the rules, you never basically get a wrong answer. First, we should write the correct skeletal structure for the molecule. And remember, molecular compounds all are non-metals. So always pay attention that hydrogen will be always terminal atoms. It means always will be in the corner. For example, like H2O. Always hydrogens will be in the corner. Never hydrogen will be in the center. Okay, because hydrogen ultimately can make only one bond because it has only one valence electron. So that's why hydrogen will be terminal atom always. And then another important thing is that always the element with a smaller count will be in the center. Even if you didn't know that, hydrogen always will be terminal because oxygen is only one element here, is going to be in the center. So always the element with the smaller count will be in the center. That's really important, guys. Like here, let's go back to here. For example, in CO2, carbon is 1, right? And oxygen is 2. So carbon will be in the center. So the first step is always make sure, see which one would be in the center and which one will be in the corners. And so let's draw the Lewis structure for H2O. So first I arrange the H2O. Then the second step would be to find the total valence electrons for the compound. Again, finding total valence electrons for the compound. So we add up basically the valence electrons. So the valence electron in oxygen is 6. And then we have 2 valence electrons in hydrogen. So we have 6 plus 2, 1 electron will be 8 electrons. You might ask again, how do you know the valence electrons in electron is 6 in oxygen? Because oxygen is in group 6A. That's why it will have 6 electrons. And when we add them up, it will be 8 electrons. Then we should distribute the electrons first between 2 elements. So here when I have arranged this, H2O, I have oxygen in the center because it's a smaller count. Then I should first put the first 2 electrons in between each 2 elements, here between O and H. So I'm gonna put each 2 electrons from these 8 electrons that I have here between each 2 elements. So how many left? 4, right? I used 4 electrons already and 4 electrons left. So make sure we cannot use more than 8 electrons than we found or we calculated in the compound. If you calculated already 8 electrons in this H2O, you cannot put more than 8 electrons. You are not allowed because you just basically discover new rules. Okay, so never ever put more than what you calculate around the element. That's really important. Then the rest of the electrons, which is 4, gonna be on the central atom. So the rest 4 electrons go to the central atom. You might ask, so why they don't go to the hydrogen? Because hydrogen has only 1 valence electron because it's group 1A, and it wants to reach helium electron configuration, which is 2 electrons. So hydrogen wants to reach the electron configuration of helium. So it cannot make more than one bond. So we cannot put more than 2 electrons around hydrogen. So the only place that is left will be in the oxygen. So let's count and let's see. After we are done, we should check the octet rule. So hydrogen, each hydrogen reach 2. See, I have 2 next to hydrogen. So these ones that are between each 2 elements are shared between 2 elements. So these 2 belongs to hydrogen. Also, these 2 belongs to oxygen. So when you count the electrons for each element, this one can be counted with hydrogen. Also, these 2 and these 2 can be counted for oxygen, and these 2 all can be counted to the hydrogen here. So pay attention to this one too. So let's count the number of electrons for each. Hydrogen has 2 valence electrons. Oxygen makes 8. It has 8 electrons around it, and hydrogen reached 2 electrons. So each of them reached octet rule. I know hydrogen reached 2 electrons, but because it's exception, we can call it also octet rule also for the hydrogen, because it has been satisfied already. It doesn't need to be 8 hydrogen. Okay, so let's do another one. So here we're gonna start again. Do you remember what was the first step? First, we should draw the arrange the elements. Always the element with the smaller count will be in the center, right? So you might ask, okay, wait, carbon is 1 element, I mean 1 count here, and fluorine has 1 count. So how I should decide which one goes in the center? So I'm just telling you, this not happens a lot. So, but if you encounter in this situation, I should tell you a very important topic here. That's the concept of electronegativity. What is electronegativity? Some elements are more electronegative. They absorb and attract electrons more toward themselves, like a magnet. You know, the magnet, when you put a magnet next to iron, it just absorbs and attracts it to itself. It's the same. They attract electrons toward themselves. So that is just their nature. So we call them more electronegative elements. So electronegativity is pulling electron toward themselves like a magnet. So let's see how the electronegativity goes in the periodic table. In the periodic table, from left to right, electronegativity increases, and from bottom to top, electronegativity increases. So in top right of periodic table, we have the most electronegative elements. So fluorine actually is the most electronegative element, is kind of the hole for the electrons. Like the black hole, it absorbs everything toward itself. So here is the most electronegative element. So let's go back to our slide. So here, when you want to arrange the elements, you make sure the element with least electronegative goes in the center. The element with the least electronegative. So if you go back, you will see that carbon is less electronegative compared to fluorine. So it's going to be in the center, and fluorine will be in the corner. Only we are allowed to put one in the center for here, for this element. for this compound. Okay, let's find the next step, find the total valence electrons. We have 1 carbon, 3 hydrogens, and 1 fluorine. The total valence electrons are 14. What was the next rule? So the first step is to distribute the electrons between each two elements. What I'm gonna do, so I have 14 electrons. I'm going to distribute them between each two elements. Then, how many I used? How many? I used 8 of it, right? So 6 electrons is remaining. So the rest cannot go around hydrogen, right? Because the maximum is already has 2 electrons, is already full. The rest should go to the fluorine to reach octet rule, because fluorine is the one that did not reach octet rule. So let's count check the octet rule in the step 4. So hydrogen is 2, this hydrogen is 2, this hydrogen is 2, carbon is 8, and fluorine is 8. So all of these elements reached octet rule. So we are done. As long as you reached octet rule, you are done. You are done with you. That's what I want in the exam. Also, another way you can write it, you can, instead of each 2 electrons, you can put a bond. So each 2 electron is like a bond. You can draw the line for each 2 electron. This is also accepted in the exam. Okay, let's do CO2. So I want you to do it yourself first. So pause here. Try to see if you can do CO2 based on the rule. So first, what we're gonna do, we're gonna arrange, put the smallest count in the center. We're gonna calculate the total valence electrons. It's 16 electrons. And then we first distribute the first 2 electrons between each 2 elements. So I used 4 of them, 12 electrons left. Make sure whenever you need to put electrons between distributed, if you are not sure to put in the center or in the corners, always first put in the corners. Always the elements in the corners or terminal get electrons first. Do you know why? Think about electronegativity. So most electronegative elements absorb electrons more, right? The more electronegative, you want to absorb electrons more. So oxygen is more electronegative compared to carbon. Do you remember the top corner of periodic table? So that's why electrons like to be on oxygens. So we are trying to put the rest 12 electrons on oxygen. So let's count them. Let's see if we have 16 electrons here. Please make sure don't go over the total valence electrons around your compound. 2, 4, 6, 8, 10, 12, 14, 16. So I used all of electrons here. Okay, but am I reaching octet rule here? So let's check. Oxygen is 8 valence electrons. Here oxygen is 8, but carbon is not, it's 4. So what should I do here, guys? I cannot just create more valence electrons because I cannot go over 16. I cannot. So please never go over what you calculate for total valence electrons. So what we're gonna do, we basically going to transfer 2 electrons from each oxygen in the corner to the bonding region, which is in the center between carbon and oxygen. Each carbon and oxygen. That's basically a rule. we should transfer 2 electrons. We just get a help from oxygen. Carbons ask oxygen, please come and help me. I don't have enough oxygen. Sorry, I don't have enough electron. So oxygen transfers 2 electrons to the center between carbon and oxygen. So it happens for each oxygen in the terminal atoms, and we have 4 electrons in the between each 2 elements. So if we go back and count the number of valence electrons, we have 8 valence around carbon, 8 valence around oxygen, and 8 valence around. So we reached octet rule. So the goal here was to reaching octet rule. So as I said, for each 2 electrons, you can put a line here. It shows the same thing. So if you draw for me this structure or this structure, is totally fine. It does not matter if the electrons are here or on top. Okay, so but make sure always show that 2 electrons should be next to each other always. Don't make them alone. The pair of electrons always should be next to each other always. So these electrons that are paired, and here they call lone pair electrons. Lone pair. So here this CO2 has 4 lone pair electrons. Okay, so what about an F3? So please pause here and try to do an F3. So first we draw the basically organize the NF3, and N should be in the center because it's a smaller count, and three F's are around. Then we find the total valence electrons, and then we begin for between each 2 elements, and we used 24 electrons. And then after we put between, we start putting around. Why we put in the terminal elements? Because they are more electronegative. So then you see that when I put around, 2 electrons left. Where do you think I should put the rest? I should put on the nitrogen. Why? Because all the fluorines are reached the octet rule, but for nitrogen is not. So the last 2 are going to be in the central atom. Or you can write down the bond, the structure of it. I accept both of these in the exam. For polyatomic ions, you are going to just do the same, calculate the total number of valence electrons. And if you have a negative charge, you add to the valence electrons. So that would be here 10 valence electrons. And we first to put in the binding first, then the rest goes to the basically a nitrogen first because is more electronegative. Then the rest goes to the carbon here. So how many valence? Let's see how many valence electrons I have. 2, 4, 6, 8, 10. So I have 10. I use all of it. Am I allowed to add just more electrons? No, I cannot go more than 10 electrons. But in another way, another hand, I did not reach octet rule. So what should I do? Double bond and triple bond. So I'm gonna transfer 2 electrons from 4 electrons, 2 each, to the center of between carbon and nitrogen to make sure my carbon reaches octet rule. So here my carbon is 8 electron and my nitrogen is 8 electron. So make sure that you should put negative charge and a bracket here. Always whenever you have a polyatomic ion and you have a charge, you should show it because you should say that where this extra electron came from. So that's from the negative that it was on top of this polyatomic ion. Okay, so please do this one, and before you see the answer, I would before looking at the answer, I do it myself, and that's the Lewis structure for this polyatomic ion. Okay, these are the examples and that I want to do. Pause here and see if we can do these structures, and then the answers are in this table. This table. Okay, guys. Now I want to talk about exceptions to the octet rule. There are some exceptions for octet rule. Group 3 elements, here B is basically exception of octet rule, is happy with 6 electrons around it. Is happy. So if you see boron in a compound is happy and basically 3 elements attached to it, it's happy with 6 electrons. Okay, so this is exception of octet rule. Also NO is another exception. Nitrogen in NO is happy with 7 electrons. So please remember those. And also SF6 and PCl5, these are also exception. Although we said that it should not be more than 8 electrons around each element, as in SF6 we see 12 electrons around sulfur, valence electrons around sulfur. Here around the phosphorus we see 10 electrons. So these are also exception for octet rule. I'm not gonna give more than is in your PowerPoint and in your book in the lecture. I mean, in your exam, basically. So what is resonancy? That's the last topic that I'm gonna talk about. In the resonancy, I want you first draw the Lewis structure for SO2. So we first make sure to find the total valence electrons. We put the sulfur in the center, and we make sure first the 2 electrons in the center, 4 electrons are used, then I put the rest of them around the most electronegative elements. Now sulfurous does not have basically 8 electrons at the end, so I'm gonna make double bond for sulfurous. Whenever you have a structure looks like sulfurous, usually this goes with oxygen, the molecules that have oxygens around them. Like here for sulfurous, I have 2 oxygen around the sulfurous. Okay, this resonancy goes with these molecules. So in these molecules, the double bonds can switch. One time the double bond can be in the left side, and one time double bond can be in the right side. Okay, so the double bond can switch. So you might ask, okay, how it is discovered? So the scientists discovered it based on the strength of the bond. Basically, the triple bond is more strong than the double bond than the single bond. So it means, like, imagine you take watermelon with 2 hands. It's more secure, right? Than you take watermelon with 1 hand. So you feel more secure, right? It's the same. Triple bond has more strong bonding compared to the double bond, compared to the single bond. But when scientists try to find the strength of these SO2, they realize that it is not like a double bond or single. This is the right one is not like a single bond. Is a between it. So each of these have 1.5 bond strengths. So then they realize that we have a switch in the double bond. That's why both of them have kind of the same strength. So this is called resonance structure. So I want you to show me the two arrow and show me if I ask for the resonance structures, show me like this in the exam. So this is also another example, like O3 is gonna switch between the bonds. Make sure that each time you switch the bond, also follow the octet rule. Okay guys, so please draw the Lewis structure or Lewis diagram for these molecules, and if it's possible, draw the resonance structures if it's possible, if there is any resonance structures. And we can pause here, and then the answer will be in the next slide. That's all for this lecture, and I will have another video about the Vesper or 3D structure later.